Let's continue our lecture on the hash function. Okay, we only have like 2 slides left, I believe. Shit. Yeah. So, previously, we have proved that if you have a universal hash functions, okay, a set of hash functions that is satisfy the universal hash property, okay, then, okay, the basically the probability that 2 given keys, okay, in the table collide, okay, it's like under H is 1 over n, which is like 1 over n squared, and there are this many pairs of keys. So basically, like you can prove that the expected number of collisions is like less than 1 over 2, so 0.5. So this is like what I believe like we stopped here last time. And then from this theorem, okay, one thing we know is that, okay, the probability of no collision is at least 1 over 2. I mean, it looks like it's like a reverse statement of this one, of this theorem. Okay, but nevertheless, we still need to prove it. Okay, so we could use this is what we call Markov inequality. Okay, so for any non-negative random variable x, we have probability x greater or equal to t is less or equal to expected value of x divided by t. Okay, this is like have been proved. Okay, to be the Markov inequality. Okay, so we make use of this inequality, okay, and set t to be 1. So probability for this x obviously is like a number of collisions. So probability for the number of collisions to be greater than 1, greater or equal to 1, is the probability of collision, okay, divided by 1. So we know the expected number of collision from here, which is 1 over 2, right? So basically it tells us that the probability of 1 or more collisions is at least like 1 over 2. Also, the probability of what should I say? Like is smaller at most. Is smaller or equal to 1 over 2. At most. Okay, so in other words, this statement is satisfied. Okay, so just by testing random hash function, okay, we can easily find one that works. Okay, what we mean by works is there's no collision, because like the number of collisions is like less than half. So just randomly, obtain like some random, some hash function from your universal hash, set of universal hash. I mean, you can easily get what you want, okay, which is collision-free hash function, okay, and also, okay, you can use this idea to build what we call like perfect hashing. In other words, like you can build like a 2-level. Okay, so the first level is from universal hashing. The second level is from another universal hashing to so that you don't have any collision, okay? But this analysis, I will skip this analysis. So this slide I will skip because like the Bucky salt, we didn't talk about Bucky salt, okay? So the analysis of Bucky salt is going to be used in this analysis, but we didn't talk about this part, so I will skip this one, okay? So basically, like that's about it for the hashing, okay? And the next one is going to be the next topic is going to be binary search tree. Okay. And the first question to you, have you learned the binary search tree from data structure? You do, right? You do. So you know what binary search tree is, right? Okay. So I'm going to skip like you know, the introduction of binary search tree, you know, and directly talk about the analysis, because like I don't think data structure talk about an analysis of binary search tree, right? So obviously like this will be, you know, something that is important in algorithm class, because in algorithm class we need to analyze the algorithm. Okay, so you know, like in a binary search tree, okay, you can use like a insert, okay, to insert each node to a binary search tree, okay, and then okay, after the insertion, I mean, you form a binary search tree, and then you perform an in-order tree work on T, which will result in a sorted list of numbers. Is that right? You know that, right? You know that. So, so here we are, I mean, giving you an example, okay? But basically, you know very well like how to do like a binary search tree insertion, okay, and in-order tree work. I mean, these are nothing new, okay, supposedly for you guys, because like, well, the data structure is a prerequisite of this class, okay? And then, okay, I don't know, like how it is covered in data structure, like because I used to teach data structure when the first 3 years when I came to like you know, NCU, that was like 2008, 2009, 2010. So it was like you know, quite a while ago, okay? But at that time, I only cover, you know, a basic idea and intuition about the binary search tree, okay? But yeah, we did cover like insertion, we did cover like obviously like for any tree data structure, we did cover like in order, pre-order, post-order, this type of stuff. So yeah, so I will skip all those like data, no, I mean, stuff that have been covered by data structure. Okay, but still, like it will be. I think it will be a good idea to at least give you an example to bring back your memory. Okay, so for example, if you are given these numbers, 318265. So the first, you are going to insert this number in this order to a binary search tree. Okay, so obviously, like originally the tree is empty, so the first number you enter is 3, right? So 3 will become the root, and the second number is 1 because 1 is smaller than 3, so it goes to the left-hand side, and then it stays there. Okay, and then 8. Okay, because 8 is greater than 3, so it goes to the right-hand side and stays there. And then 2. Okay, 2 is smaller than 3 and it's bigger than 1, so it stays here. Okay, and then 6, goes here, and the 7, okay, it's greater than 3, smaller than 8, greater than 6, so it goes here, and so on for the 5. So we know, this is how the insertion works. Okay, and I believe, like in data structure class, the teacher will tell you that, okay, because it's a randomly insert. Okay, you don't know like the sequence, so most likely this insertion will result in like a roughly balanced tree. So as a result, the height of the tree after the insertion will be log n. So, since insertion, okay, this tree insert is proportional to the height of the tree. So this operation is log n, and you have like n. You are going to do this n times, so this is n log n, and then in order of tree work, it takes like a linear time. So I don't know, like in data structure, they would probably just tell you, oh, it's n log n. Okay, which I believe like most of you are satisfied with this intuition, right? Okay, so, but how do we formally analyze this? At least we want to know like some way to formally analyze it. Okay. So this is like the topic of today's lecture. Okay. So I hope like you guys still remember the analysis of quicksort, right? Because we did that like just a couple of weeks ago, like right before the midterm, right? Okay, so basically, okay, let's think about this thing. Okay, this is an example I just tell you, right? This is an example I just told you, like 3182675, and it results in this binary search tree, right? Let's forget about the top. No, the statement at the top, okay? Think about this. After this after we insert 3, okay, 3 is the first element. After the 3 is inserted, all these numbers will have to be compared with 3 to determine it's going to be on the left or on the right. Right? And all these numbers, regardless their order, all these numbers that are on the left of the 3 are smaller than 3, right? All the numbers that are on the right of the 3 are larger than 3. Okay, after the comparison with 3. don't you feel it is similar to like a quick sort? What do we do for the quick sort? In the quick sort, we get the first element, and then we treat the first element as a pivot. And we need to find a place that, for this pivot such that elements on the left-hand side of pivot are smaller than the pivot, right? Elements on the right-hand side of pivot are larger than pivot, right? 在那个 quick sort， 我们是不是把第一个 element 当做 pivot， 然后呢，我们经过一轮的比较以后，我们找到一个位置，把 pivot 放过去，然后所有在 pivot 左边的都比 pivot 小，所有在 pivot 右边的都比 pivot 大，对不对？对不对？大家想想看这个，再看看这个东西，哎，好像是不是差不多？ It is similar, right? Because, at the end, after we insert this, finish the insertion of this binary search tree, 3 is sitting in the middle, okay? And on the left-hand side, locate the numbers smaller than 3. And on the right-hand side, okay, the right subtree has the numbers that are greater than 3, right? So that, but of course the timing that comparisons happen, okay, between 3 and all these elements is different from the quick sort. 在那个 quick sort 里面呢，大家都会想一下哦，我们 pivot 我们选定1。 然后之后我们就我们去找比它小、比它大的，然后做一些调整，对不对？然后最后把 pivot 放过去，对不对？那个是在好放过去以后，3就不动了，对不对？剩下就不用跟3没有关系了，对不对？对不对？好，那但是这边呢，这边你3先放着，但是随着你一个一个加进来，你一个一个是不是跟3比？然后再决定在左边还是右边，对不对？所以说比那个 comparison 的时间是不一样的，对不对？ 但是 comparison 的number of comparison stays the same, right？ 比较的次数还是一样嘛。原来在你的 pivot， 你是跟 pivot 比，你现在是说你先放中间，然后一个一个跟3比，然后再决定在哪边。但是那只是说比较的顺序不一样，但是你比较的次数是一样的，对不对 ？You can try to think. I mean, for this number as well, you are going to insert 6 first. You are going to insert 6 first. 6 appear before 7 and 5, right? And then you insert 7, you insert 5. Obviously, when you are done with, so in this sub list, okay, you are using 6 as the pivot. Okay, and then in the final, in the last few insertion, you decide 7 should appear on the right hand side of 6, and the 5 should appear on the left hand side of 6. 这个跟那个 quick sort 也是一样的，对不对？对，所以说其实 ，okay, basically binary search tree sort, okay, or binary search tree insertion. Basically, it performs the same comparisons as quick sort, but in different order. The number of comparisons, is the same. It's just like in a quick sort, we deal with each number, separately, and then we find the location of that number. And then the number stays there for good. 那个数字就不会再动了 ，OK？ 那我们找到一个地方给 pivot 放在那边以后，那 pivot 就是那个位置就是对的，就不会被动了。但是这边呢，我们是 OK， 一开始先放个数字在那边，然后再做比较，再跟后面的数字做比较，这样子。所以这个 comparison 是后面才发生的，但是basically 那个数字比较的数字是一样的。 所以呢 so basically, okay, from this argument, from this, once you understand the essential idea, okay, of the similarity between the binary search tree sort and the quicksort, you will understand like the expected time to build a tree must be asymptotically the same as the running time of quicksort, right? 一定一样嘛，对不对？如果不一样，你就有问题了嘛，就会有问题。好，接下来是要讨论一些分析哦，譬如说第一个 ，the depth of a node， 或者 another way to say it is the number of comparisons made during tree insert. Okay, so here we assume all input permutations are equally likely. Okay, this is if you check out this sentence is equivalent to the randomized version of the quicksort. Remember, in the randomized quicksort, we first try to randomly permute the numbers first, right? And then do the quicksort. So basically, okay, here I mean we are trying to assume the same thing as the quicksort. And then we have the average node depth will be, the 1 over n, because like we have n numbers, so we need to average it, okay? So expected number of comparison to insert a node I, okay, the sum of that. And we know this one, because as I previous told you guys, the comparison basically, is the number of comparison is the same to the quicksort. It's just like the order is different. So we know like the total number of comparison is n log n, okay, and then we try to average this value by n, so we get like log n, okay. So basically the depth of a node or the number of comparisons that happen during the tree insert in the binary search tree is big O log n. So this is wonderful, right? This is wonderful. I mean, in a data structure, I mean, the teacher will just tell you the intuition. Even the teacher usually will not tell you like unless it's a very simple proof, theorems, okay? Otherwise, like the teacher usually skip the analysis. But here we are trying our best to, to give you the analysis. That's the difference between the data structure and this class, okay? And I hope you guys learn the how to analyze the algorithm, okay? And then, okay, how about the average? We know like average node depth, or like from the previous analysis, average node depth is log n, big O log n. So it's nice, okay? But it doesn't necessarily mean that the height of the tree is big O log n. What's the difference? What is the difference? Okay, because, okay, the average height, average depth of the tree, of a node, is different from the height of a tree, because height of a tree is, is dominated by the largest depth. It is not dominated by the average. Okay, so here we try to give you an example. In this example, you can see that, okay, we have like most of the nodes have the depth less or equal to the log n. Okay, there's only one branch. This branch, the depth is square root of n. Okay, square root of n. So what in this tree, what is the average depth of the node? The average depth of the node, okay, you can see that, okay, most of them are log n, right? Most of them are log n. Okay, so it's n log n. And for this branch, we have n nodes. And their height is up to, not n node, sorry, square root of n node. And the height is, square root of n, okay? I mean, from 1 to square root of n. So it's like, the average is like half of this, right? Half of square root of n. So it's square root of n times like half of square root of n. That's the average height for the nodes on this path, okay? So if you average this, the average depth will be, small or equal to 1 over n to this one, right? So it is still log n. Okay, so we could have a tree. Its height is obviously square root of n, right? Square root of n is obviously, different from log n, right? I mean, the order is very different, right? But the average node depth is log n, right? 所以这个就是一个例子哦，我们可以有那个每 node 的那个平均的 depth 是 log n， 但是树的高度是 n square root of n， 就是 n 开根号。那我们知道 n 开根号的 order 跟 log n 是不一样的嘛，对不对 ？n 开根号的这个 order 比 log n 还大得多，对不对？对，所以说这边就告诉大家说，就算是我们证明了说这个 average node depth 是 log n 哦，这个并不代表说我们可以说expected tree height is big O log n。虽然直观 intuitive speaking， in data structure I will just tell you, okay, according to intuition, yeah, this is the case. I will not go any further beyond this point. Okay, but this is the algorithm class, so we have to continue, digging in. 所以我们必须要去分析这件事情哦。所以今天我们会花比较多的时间在这个上面。OK， 这是一个比较大的一个分析哦。好。这个分析哦，其实是比较复杂的 ，OK。So, because this analysis is complicated, so we even give you an outline, a sketch of this proof. Okay, so this proof, okay, the whole proof consists of 3 steps. Okay, 3 steps. First, we need to prove the Jensen's inequality. Okay, basically, for any convex function f and the random variable x, okay, f of ex must be smaller or equal to e of f of x. So we need to prove Jensen's inequality first. And then we need to analyze the exponential height of randomly built binary search tree. okay, if you have n nodes, okay, and then you will we'll be able to show that the expected height, expected exponential height, okay, will be big O n's cube, and then because it's an exponential height, right? So once you use the log, it will tell you that e x n, the height of the tree, expected height of the tree, is big O log n. So it's like a kind of like a very indirect proof. We will even discuss why we need to talk about the expected height. Not why don't we just directly talk about expected height, okay? So, I know like in previous, for example, like a Markov inequality, we didn't prove that, right? Because that's a little bit too much out of the scope. But this one is really not that difficult. And also like it will be good to understand like what the convex function, what's the definition of convex function. So obviously like you probably don't know what convex function, the definition of convex, the definition of convex function. Okay, so we need to bring up the definition of convex function first. So a function, okay, let's assume that's from a real number that map to a real number. So it's a very simple function that you have learned from high school, okay? So a function is defined to be convex if for all alpha, beta greater or equal to 0, okay, such that alpha plus beta equal to 1, okay, we have alpha x plus beta y smaller than or equal to alpha fx plus beta fy for all xy greater, in the range of R. So this is like, if you draw a figure, so if this red line represent that function, okay, and you have x, you have y, the alpha x and the beta, alpha x plus beta y, obviously is the interpolation in between x and y, right? 它是一个内差嘛，对不对 ？x 跟 y 的内差，所以它发生在 x y 之间，所以 f of alpha x plus beta y is here, and fx and fy, the interpolation of fx and fy happen here, right? 就是这个是内差，这个值的内差，这两个值的内差，这是这个内差以后取值。他意思就是说，哦，它是 convex， 就是如果说它是这样子的，就是你这边随便画一条直线，每个直线中间的点都要大于这下面这个白色这一块，这叫 convex， 这叫 convex。Okay. In other words,我们真是很穷。来找一下。Okay, good. In other words, this is not convex. Okay, obviously, because in this example, this number and this number, they are, they're supposed to be, you know, just like here. But here, I mean, it's obviously like the other way around. OK， 就是这两个值的内插出来的值，应该要比这个内插出来取function的这个值来的大才对。它这边比较小。Another way to another possibility is like this. This is not convex either, okay? Because convex function, we need to guarantee this property for all the you know the I mean all the range of okay, range of the function, okay. So this is obviously like you know, this is convex, but this part is not. So this function is not convex. So can someone give me like some example of convex function? Can someone give me some example of convex function? X squared? Yeah, x squared could be a convex function. Yeah. Anything else? So for example, exponential of x, right? It's also convex, right? Okay, good. So first you need to know the definition of convex function. And then let f, okay, I mean be a convex function. Okay, that we have a convex function, and that alpha 1, alpha 2, to alpha n be non-negative real numbers, okay, such that the sum of these numbers is 1. Then for any real numbers, you know, for any such a set of real numbers, we have this. So this is kind of like a generalization of like a convex property, right? So you get like a, you know, kind of like a, I probably shouldn't use like a interpolation, but it's like a, x1, x2, x up to xn, you know, multiplied by alpha, by alpha I, and the sum of the you get the f value from the sum of these numbers, and this is guaranteed to be small or equal to, you know, for each fk, each xk, you get the function, the f value, and multiply by alpha k, and you sum them up. Okay. So how do we do that? This obviously, you know, the first thing you could think about is the induction, because when you have two numbers, alpha 1, alpha 2, and x1, x2, this is exactly the definition of, you know, of like the convex function, right? You can even start with one number. If you have only one number, this one is smaller or equal to alpha 1 fx1. This is also trivial. This is also trivial. So for one number, for two numbers, okay, because the function is convex, so we have this for sure. But I mean, beyond that, what do we do? Okay. So let's do this, induction step. So we know this is going to be, you know, if we have like from 1 to n, okay, this alpha k, xk, you know, we can, you know, get the last term out here. And this is from the first term to n minus 1 term. We can have the rest of term here. But with a twist, what do we mean by a twist? Because we can have like this a number divided by 1 minus alpha and we outside here we multiply 1 minus alpha n. This is obviously no problem, right? This is the same. This is the same as this one. Okay, this is simple algebra, right? But obviously, this alpha n is a positive number. 1 minus alpha n is also a positive number, right? And the sum of these two numbers will be 1, right? Okay, so then, okay, from here, okay, the next one is we can apply the induction hypothesis to say, oh, this one, okay, the other one stays the same. The other one stays the same. Okay, so, well, actually, we apply like a 2. This is according to the convex property because we treat this as 2 terms. So for 2 terms, we have this one, small or equal to alpha n fxn plus 1 minus alpha n f of this one. I mean, because this function is known to be convex, okay? And then we try to apply the induction hypothesis, okay, to here, okay? So the small equal sign still holds. So this one is the same, this one is the same. The only thing that gets changed is here. The summation, is moved from inside F, okay, to outside F here. And of course, alpha k is also here. So we have this. And then, okay, we multiply this back to here. And then, we can put everything together to become this one. This is simple algebra. So we have this one, okay, small or equal to this one, right? And in between the process, we apply the convex property, we apply induction hypothesis. So, okay, if you have like a n number of elements, and if you have n number of this alpha, and they are all positive, and the sum is 1, then we have this generalized version of convex property for convex function. But we need to further generalize it. We need to further generalize it. Why? Because the previous case is a finite case. We need to prove the infinite case. Yeah. Well, let's take 10 minutes break. When we come back, we will continue the discussion. Okay?